Welcome to episode 3, Minerals. And today, I'm going to talk to you about what a mineral is. And here is a modified definition of what geologists use. Don't worry about it. Don't bother memorizing it because I'm going to explain it here. Minerals. Minerals fit a very stringent, tight definition. We, as geologists, use a tighter one than the one I'm about to give you and a longer one. But for intensive purposes, for this level, this is what we're going to talk about. Minerals have these properties all the time. I know there's a usually here. We'll get to that. But minerals are the building blocks of all rocks. The technical term in geology of rock is rock. It's just what you think of when you think of a rock. Except it does include some things you don't think about. In geology, we do not differentiate between consolidation, how hard a rock is. Loose sand on a beach, we treat as a rock unit, just like we treat this as a rock. And there's reasons for that, but those are talks for other times. Now, a mineral is always naturally occurring. So if you grow a mineral in a lab, or glue two rocks together, you don't have a true mineral. They have to be naturally occurring, and that is also talk for another time as to why that is. They always form crystals. Now there's something we consider rocks that don't form crystals, but we're not going to talk about those. I can mention them. Mineraloids are one, and coal is a big one. They have to be inorganic usually. We'll get back to this one. And they are always in solid state. Real quick. Inside the earth, you have different layers, and the mantle, which where a lot of magma and molten lava is derived from, it's actually a solid. It melts when pressure is released or if there's water added to it that lowers the melting temperature. But as a rock melts or starts to solidify from a melt or magma, there's a gray area in there. We do not include that gray area, and I'm only going to touch on this real briefly. Why don't we include that gray area? Because there are no stable minerals in that gray area, or very few stable minerals, I should say. Not always. There are some. But like when a granitic rock, like this one here, okay, as that cools from a magma, if certain minerals will form first, because as it cools, certain melting points have been passed and it can form a solid. But in that gray area, there's a group of minerals called plagioclases. Plagioclases are not stable while still in that gray area. As they cool, some will stay plagioclase, but some will become what we call alkali feldspar or K-spar. So that's why we don't include the gray area. So you must be solid. So what's up with this usually? All right. Touch on this real quick. Quite honestly, it's an 18th century holdover, 1700s. As what we now call geologists and biologists started actually looking at rocks and things like that, making what would eventually become geology. Back then, geologists and biologists were called naturalists. And geology started to emerge as a science based on observation, and you can do experiments in geology. So it started to move along as an actual science. But when people were out there looking at stuff in the world, earth materials, natural earth materials, which include rocks, but also includes rock units, not well indurated, coals, things like that. There's a certain type of rock that technically isn't inorganic, that's really, really common. But back then, we didn't have the microscopes or the tests or the analyses we have today to determine chemical composition of rocks. That we have to wait like 100 years or so until the late 19th century, mid-late 19th century. People would just go out and they would say, oh yeah, that's a rock. It formed naturally, looks like a rock. It has layers in it like other rocks, this and that. But along would come organic chemistry, and just so you know, in chemistry or science in general, something that's organic isn't what you would think of as being organic, like at a grocery store. That's a marketing term. That isn't what organic means in science. In science, anything technically that has a carbon molecule, which we are carbon-based life forms on Earth, is organic. Well, there's a real common rock that contains carbon that we consider a mineral, and it does form crystals, and I'm going to show those to you, but we don't consider it organic. And the big exception to this, and I've already mentioned it, is calcium carbonate, CaCO3. Calcium carbonate is a compound that forms calcite. Calcite forms limestone. There's dolostone, which is also real common, made of dolomite, which has magnesium and calcium in it. And I'm going to show you some of that here in a second. But this is an exception. And it's, like I said, it's part of that holdover. Because limestones have been known and studied scientifically since the 18th century, essentially, maybe a little earlier. But we didn't know what their chemical makeup was. That came later. So they've always been treated as a rock and a mineral, so we treat them as rocks and minerals. Here I have a piece of Precambrian carbonate rock. This is from the Randville Formation. It's from the Upper Peninsula of Michigan. It's very old, and this is mostly a dolostone made of dolomite. Now, the beautiful thing of calcite is when we start talking about mineral identification, there's something that really identifies it really well. Now, when we think of limestones and dolostones, we think of sedimentary rocks, and there's three types of rocks. There's igneous, sedimentary, and metamorphic. And you may be familiar with this as sedimentary rock, but we also have igneous carbonates, and I own one that also is from the Upper Peninsula. So carbonates can form in multiple environments, but talks for other times. But what you see here, this is from a geode in Indiana, southern Indiana. The rock around it is limestone. This is Paleozoic. I don't know the exact age. Ordovician, maybe Silurian. But what you see in it are these awesome white crystals. Those are calcite crystals. You see smaller crystals within it, which I have never bothered to identify. They do fizz, so there's some sort of carbonate. They could be siderite, or they could be dolomite. But you can see these minerals form crystals, and this is natural. This is a quartz crystal from Arkansas. Quartz has different varieties that geologists don't use terms like amethyst. That's a collector's gemstone term, but basically amethyst is purple quartz, and I have some of that too from Canada. You look at this and you can see some things about it. You see it's got a point at the top. You look at it from the top, it has 6 sides. We call this hexagonal. This is the hexagonal crystal. There's 6 or 7, depending on who you ask, crystal systems. I'm one of the people, I'm old enough to where I was taught if there were 6, but they pulled another one out, making it 7. As far as I'm concerned, it's potato stuff. That's classification. I'll accept the 7. It bothers me not. This is hexagonal, and you can see how it breaks. There's lines on it. It's not a perfect crystal. It is imperfect, but this is really good for nature, and this is naturally occurring. And we're going to get into what some of these lines are in a later episode. Crystals form from compounds. If you remember in the chemical compound part, I talked about internal atomic arrangements, the way the elements bond together to form compounds. And if you keep throwing them together and more and more and more, well, eventually you get something like this. This forms this crystal based off its internal atomic structure. Minerals can also be individual elements like this. It's copper. I've already shown you this. So minerals can be elements or compounds, but they always have these characteristics, with the exception of this, which we put carbonates in with, for reasons I've already explained. But anyway, I think I'm going to wrap this episode up. If you have any questions or comments, feel free to ask your teacher.